Calculus 4.6, approximating values of a function using tangent lines. And they're going to give you an equation and ask you to approximate the value of the tangent line of that equation at a specific x value. Given f of x equals 3x plus 1, find f of negative 1 and f prime of negative 1 and write the tangent line at f of negative 1. And use the tangent line approximation to estimate f of negative 1.1. So in this example, they give us f of x equals 3x plus 1. And they want us to find f of negative 1. So if I do that, that means I just plug negative 1 into that original function. So 3 times negative 1 is negative 3 plus 1 is negative 2, which is an ordered pair, negative 1, negative 2. So the ordered pair at negative 1 for this function is negative 1, negative 2. They want us to find f prime at negative 1. F prime of x is what we get when we take the derivative, and that would just be 3. And so we know from our previous knowledge that the derivative of a function at a specific x value is the slope of the tangent line. And if I plug negative 1 into this and get f prime at negative 1, I would still have 3. So that gives us enough information to write the tangent line at f of negative 1. We can plug that into point slope form to do that. Remember, point slope form is y minus y1 equals m times x minus x1. Y plus 2 equals 3 times x plus 1. So we have the tangent line of f of negative 1. The next thing they want us to do is use this tangent line to approximate f of negative 1.1. So if we convert this to slope-intercept form, we have, so f of x equals 3x plus 1 would be our tangent line of the equation, and they ask us to find f of negative 1.1. When I do that, I get negative, so the estimate for f of negative 1.1 is negative 2.3. In this example, they give us f of x equals 1 over x, and they want us to find the tangent line equation at f of 2, and then approximate the value of f of 2.1. I could plug 2 into that function to get f of 2. I get f of 2 equals 1/2, so that's an ordered pair, 2, 1/2. To find the equation of the tangent line, I have to find the slope of the tangent line. To find the slope of the tangent line, I have to take the derivative. So if f of x equals 1 over x, I can rewrite that to make the derivative a little bit easier. F of x equals x to the negative 1. And then to take the derivative, f prime of x is equal to negative x to the negative 2. And I could simplify that as f prime of x equals negative 1 over x squared. And then I could plug 2 in to find the slope of the tangent line. So when I plug 2 in, I end up with negative 1/4 as the slope of my tangent line. So I have the ordered pair 2, 1/2 and the slope of negative 1/4. So if I put that in point slope form, I have y minus 1/2 equals negative 1/4 times x minus 2. I'm going to put that in slope-intercept form. I'm not sure this is really necessary to put in slope-intercept form, but they're asking for the value of f of 2.1, and I think that would be easier to do it in slope-intercept form. So 1/4, or negative 1/4 times x is negative 1/4 x. Negative 1/4 times negative 2 is a positive 1/2, and if I add this 1/2 to it, that'll be a plus 1 on that side. So we have y equals negative 1/4 x plus 1, and we need this as a function, so that would be f of x equals negative 1/4 x plus 1. And they want us to find f of 2.1. So if I plug 2.1 into that function, I end up getting 0.475. In this one, it says find the local linear approximation if f of x equals the cube root of x and x equals 8. Use it to approximate the cube root of 8.1 to 3 decimal places. So they've disguised this problem a little bit. If you think about what they're asking you to do here, they want you to find the local linear approximation. So they're asking you to find the equation of the tangent line here. The equation that they gave you was f of x equals the cube root of x. And they want you to use that approximation to find the approximation for the cube root of 8.1. Now, if you think about that, if our function f of x is the cube root of x, And they've asked us to find the cube root of 8.1. Haven't they asked us to find the estimate for f of 8.1? Isn't that what we would get when we plug it in here? So this is really asking us to do the same thing that the last two examples ask us for, but it's just kind of disguising the wording a little bit. So if f of x equals the cube root of x, to take the derivative of that, I'm going to rewrite it first. That's x to the 1/3. And then that means that f prime of x, the derivative, would be 1/3 x to the negative 2/3, which means f prime of x is equal to 1/3 times x to the 2/3. And they asked me to approximate f of 8.1 by finding the local linear approximation of f of x equals the cube root of x when x equals 8. So they want us to find f prime of 8. We'll have to find the slope of the tangent line at 8. So if I plug 8 in for x, well, 8 to the 2/3 power, that would be 2 times 2, or 2 squared would be 4, times 3 is 12. So that's going to be 1/12 as the slope of my tangent line. If I want the ordered pair when x equals 8, I need to find f of 8, which is 2. So f of 8 equals 2, giving me an ordered pair of 8, 2. So the equation of the tangent line, so we know f of 8 equals 2. We know f prime of 8 equals 1/12. So if I need to find the equation of the tangent line, I would use point slope form. So that's y minus 2 equals 1/12 times x minus 8. And then to get that in slope intercept form, y is f of x equals 1/12 x minus negative 8 times 1/12 is negative 2/3, and negative 2/3 plus 2 ends up being a positive 4/3. So that'll be a plus 4/3. So that is the estimate for the tangent line when x equals 8. And so then I take that estimate for the tangent line and I will plug f of 8.1 into that. So f of 8.1 is equal to 1/12 times 8.1 plus 4/3, leaving me with f of 8.1 is equal to 2.008. In the next couple segments, we're going to consider slope of tangent lines of curves. And specifically, they want to know, how are we going to know if the tangent line is above or below the curve of a function? And in order to kind of figure that out, we need to talk about different properties of the function. If you look at this one, it looks like it has two curves here. This one has a minimum, this one has a maximum. And if we think about the slopes of the tangent lines as we go around that curve, if I were to choose a point over here, like let's say right here, well, my tangent line would be negative. Let's say I choose a point here. Again, that tangent line is negative. Let's suppose I choose the point at the minimum there. Think about that tangent line. Wouldn't that be the tangent line of 0, or have a slope of 0? And then if I choose one here, well, again, that's positive. It looks like to me, maybe right around here, we have a change in concavity, meaning it's concave up until we get to about that point, and then it's concave down after that point. And that's something you should have talked about a little bit in pre-calculus. We extend that knowledge in calculus pretty soon. And then let's talk about the slope of tangent lines on this side of the curve. If I do this one, the slope of that tangent line will be positive. If I go to the maximum here, that's going to be a slope of the tangent line of 0. And if I go here, that's a negative slope. And here, that's a negative slope. So if you look at this, the slope of the tangent lines here, aren't they increasing? The slope of the tangent line, this one, is a pretty steep negative slope. I didn't draw that very well. This one is a less steep, a more gradual tangent line. This tangent line right here is 0. This tangent line is positive. So look at what's happening to our tangent line slopes as we move underneath this curve. Aren't the tangent lines, aren't the slopes increasing? So when our slopes are increasing, our tangent lines will be drawn below the actual curve. Look at what happens on this side. This tangent line is a positive slope. At the maximum, it's a zero slope. Here, our tangent line. Here, the tangent line is a fairly gradual negative slope. And here, the tangent line is a rather steep negative slope. So if you look at the lines that are drawn above the curve, those slopes are gradually decreasing. So when your tangent lines are drawn below the curve, your slopes are increasing. When your tangent line is drawn above the curve, your slopes are decreasing. And another thing they'll ask you to think about is when your slopes are drawn above or below the curve, are they overestimates or are they underestimates? Well, that's a pretty simple thing to figure out. If your line is drawn above the curve, you can consider that since it's above the curve, it's an overestimate. And when your tangent line is drawn below the curve, it's below the curve, so you can assume that that is an underestimate because it's drawn underneath the curve. Another thing that we will talk about as we move forward with calculus is this point right here is where the change in concavity occurs. And now we have talked about the different slopes of the tangent line, and we've talked about when the slope changes from a negative to a positive, we have to have a zero in the middle, right? And that zero slope, a horizontal tangent line, separates the negative slopes from the positive slopes. The opposite effect is true on a curve that is going in the other direction or is concave down. The slopes go from a positive slope to zero to a negative slope. And that directional effect of slopes becomes very important when we deal with graphing the derivatives and graphing the second derivatives of equations. Another thing you need to understand is if your function is concave up, the second derivative has a direct correlation between that being concave up. If it's concave up, the second derivative is positive. If it's concave down, like it is here, the second derivative is negative. So concave up, f double prime is positive. Concave down, f double prime is negative. Well, let's talk about what happens at this spot where this function changes from concave up to concave down. If concave up is positive and concave down is negative, wouldn't the second derivative at the inflection point or where concavity changes have to be zero? So the second derivative is zero when the inflection changes, or when it changes from concave up to concave down, or vice versa, concave down to concave up. So here's another function. It says for the given graph, use the slopes of the graph to discuss concavity of the graph, then talk about what the graph of f prime and f double prime would look like. Well, this is your graph of f. There are a few things we know about the graph of f. It looks like right here at A, we have, if we draw a tangent line there, that would be a horizontal tangent line. Looks like there's a maximum there. It looks like here at C, to me, we have another horizontal tangent line that is a minimum. Looks like to the left of A, our slope is positive. Between A and C, it looks like the slope of our tangent lines are going to be in a negative direction. To the right of C, it looks like the slope of our tangent line is going to be in the positive direction. So let's talk about what that means. It looks to me like in here somewhere there is a concavity change. This is concave down to our concave up. So let's talk about if this function in black, and let me just write this in black, if that function in black is f of x, I'm going to draw f prime of x and f double prime of x using different colors. I'm going to use red to draw my f prime function. Now, what I know about f prime is the slope of the tangent line at A is at 0. That means my f prime graph will cross the x-axis at A. The slope of my tangent line at C is also 0, so that means it's going to cross the x-axis again at C. So my f prime graph, I need to consider what happens with the slopes and how the slopes are changing on my f of x function. To the left of A, remember A crosses the x-axis at A and it crosses the x-axis at C, meaning the derivatives are 0, or the slope of the tangent lines are 0 at those 2 points. Wherever the maximum and minimum are held in your f of x function would be the points where the line crosses the x-axis on our f prime graph. Here, the slope of the tangent line is positive to the left of A. If the slope of the tangent line is positive to the left of A, and all of these tangent lines would be positive to the left of A, then that means my derivative is going to be above the x-axis to the left of A. So my derivative is above the x-axis. I don't know how steep that graph would be, but I do know all of these points on my f prime graph to the left of A will be positive above the x-axis because their slopes were positive. Between A and C, I don't know a whole lot about where the f prime graph is going to be, other than every one of these slopes between A and C is negative. So between A and C, my slope will be underneath the x-axis. And then to the right of C, all of my slopes, if you look at that, are positive. So to the right of C, my f prime graph is going to be positive above the x-axis. So the red graph there is the graph of f prime. Notice one thing about this is it looks to me like the point of inflection would be about here at B. And look at the f prime graph. It looks to me like that's where my minimum is for my f prime graph. Another thing I notice is this function has 2 curves, so doesn't that mean it would be an x cubed graph, a cubic function? Look at the derivative function. That looks like a parabola to me. So that means it would be an x squared function. So when you go from the f function to the f prime function, the degree of that function is going to decrease by 1. All right, so now I'm going to change colors, and I want to talk about f double prime. So what we're going to do is we're going to consider the slopes of the f prime function to determine how to graph f double prime, and I'm going to do that in blue. Well, it looks to me like if I were to draw the slope of the tangent line at B, that would be a 0 slope. So my f double prime graph will cross the x-axis at B. To the left of B, look at the slopes of the tangent lines. Looks like they are all negative. So that means to the left of B, all of my slopes are going to be negative. Look to the right of B. It looks like there, all of my slopes are positive. So to the right of B, my line will be a positive above the x-axis. So my f double prime graph is a straight line. It's linear. Any linear function has a degree of 1. So again, that inference of the degree decreasing by 1 every time we go to a different function is true. So my f graph was a cubic, a 3rd degree function. My f prime graph was a 2nd degree function. And my f double prime graph has a degree of 1. So my degree does go down by 1 each time. Another thing it's important to notice is look at my f double prime graph at the point of inflection where the concavity changes. That's where my f double prime graph crosses the x-axis. So that gives you a quick introduction to graphing a function and its first and second derivative. You will get more practice with that along the way.